Now let's talk about the diffraction pattern produced by a diffraction grating. So what is diffraction grating? You can think of a diffraction grating basically as a board with plenty of slits in it. Okay, so the slits are usually aligned parallelly, but there's plenty of slits within an opaque board. So when you shine light on it, there's plenty of slits here where the light will be able to pass through. So you can think of each slit here to be a single, you can think of each slit here to be an infinitely narrow slit. So something like a double slit, but double slit has 2 slits, but this one has many slits. Okay, so we call this board here as a diffraction grating, but the slits here is not on the order of 2 or 3 or 4 slits or even 10 slits that you see here. When we talk about diffraction gratings, right, it's usually about hundreds to 1,000 slits per cm. So within one single cm, you have about hundreds to thousands of lines or thousands of holes in it. So it's a very narrowly arranged kind of hole. And if you shine light, let's say from this side, you shine light towards the diffraction grating and you place a screen somewhere here, the kind of pattern that you will observe on the screen is it will be a very bright sharp maxima. We usually call it as maxima, or bright fringe is probably, I seldom use the word fringe, I will call it as maxima because it's very sharp and it's very narrow. It's not similar to the diffraction it's not similar to the double slit kind of dark bright that is very regular in terms of size. This one is a very sharp bright, then afterwards you see a dark region, a very white dark region, followed by a next very sharp maxima, a sharp bright spot, then afterwards a dark region. It's usually a bright spot followed by a dark region and another bright spot followed by another dark region. Okay, so the pattern is definitely different from what you will observe from a double slit interference or a single slit diffraction. Both of those are actually a bit more uniformly spread out, This one is a bit like a sudden bright, then a dark region, then a sudden bright, there's the dark region over here. Okay, but why do we get to have this kind of pattern, right? It's because at these kind of bright spots over here, you get to have a constructive interference happening at these positions over here. So every position that you see a bright spot is the position that you see a constructive interference. But those dark regions over here are basically many of the pairs of slits here producing wave that cancel each other out. So when they cancel each other out, basically those light will not be able to arrive on the screen. That's why it appears at the dark region. Okay, so we are going to focus on those bright spots over here, or the bright maxima over here, because we know that there's constructive interference happening there. Okay, it doesn't mean that these dark regions here is totally destructive interference. If it's totally destructive interference, right, you will not see these kind of things over here. You can see a bit of zigzaggy line over here, means by there's a little bit of light that ends up arriving on the screen. So it's not fully destructive, but it's very significantly destructive, I would say, but not completely destructive. So there's still some amount of light that arrive on it. Okay, but those are not our concern, because these dark regions here, if you want to place a Y, let's say a Y that we measure from central, where do you want to place our Y for this dark? Place in the middle, place somewhere up here, place somewhere down here. It's very hard to measure the Y, right? So we don't usually measure the Y for the dark region. We only measure the Y for the maxima, okay, which is this spot. We can drag from the central up to this spot, then we can say that is Y. Or you can drag to the next maxima, then we say that's the next Y. Okay, so Y is usually for the maxima in diffraction grating cases, and now we'll be deriving the equation for diffraction grating. Okay, so you can basically think that if we manage to get the bright maxima over here, what it means is that all the light that shines, all the light wave that comes out from each of these slit here, each of these slit, there will be light wave emitting in circular wave out from all of these slits, right? So all these wave over here, when they arrive at this spot over here, they will all interfere constructively. Okay, they will all form pairs that constructively interfere. So that's why the resultant of it will be a very strong maxima, a very intense bright spot on this area, on this spot over here. Okay, so why is it true that you get a constructive interference here? We might need to zoom in and look at it near to this side over here. Okay, right now you see that the lines sort of form a very small triangle over here. All these lines are forming a very small triangle over here. But if you try to zoom in to look at it from a closer look at it, you see that all of these lines seems to be about parallel to each other. and if you can recall back to the double slit experiment, that is what I talk about. Okay, when you focus very near to the slit over there and you place the screen somewhere that should be far away from the slit, these rays that we draw over here, or the light wave that is traveling over here, or the path from the slits to the spot over there, these paths will sort of be parallel to each other. You can see over here is sort of parallel to each other, even though if you zoom out and look at it, it is not parallel to each other. But if we try to focus on the region that is very near the diffraction grating, you see that they're actually parallel to each other. Okay, we approximate it to be parallel to each other. Okay, so if we approximate to be parallel to each other, right? So if you want to compare the path difference between the first two paths over here, let's say this one is R1, this one is R2. If you want to compare the path between them, the difference will be only this small little portion over here. Okay, maybe I zoom in even further. If I want to compare what's the length difference between path 1, which is R1, and path 2, which is R2 over here, you can think of it, they arrive at the same destination. So these from here to the end of the screen and from here to the end of the screen should take the same distance. So that means by the extra distance traveled is actually this small part only. Okay, this is the small part. This is a small extra distance traveled by the light wave coming out from the second slit when compared to the first slit. Okay, so if this slit over here, if this extra distance here, which is R2 minus R1 effect, essentially, if this small distance here is actually 1 lambda, okay, if this small distance here is actually 1 lambda, that means by the path difference between R2 and R1 will be 1 lambda. If R2 minus R1 is 1 lambda, that means it's an integer multiple of lambda, right? So if it's an integer multiple of lambda, which is in this case 1, m is equals to 1, then it will be constructive. It means by the light coming out from the first slit will interfere constructively with the light emitting from the second slit. These two slits, their light will constructively interfere. Okay, so if you use the same logic over here to continue the discussion on the next slit, which is the third slit over here, you should also expect that the second path R2 and the third path R3 over here, they should also differ by this one single lambda over here. So you should expect that from here to the end is the same length as from here to the end. So the extra distance traveled will be this small part over here, and I believe you can see that it's equidistant to what we label above, which is 1 lambda. So here it should be 1 lambda. So right now the path difference between the first path and the second path is 1 lambda. The path difference between the second path and the third path is also 1 lambda. And if you compare between the first path and the third path, the first path and the third path, their difference in path is 2 lambda. Okay, so you can see that the path difference is always an integer multiple of lambda. If you compare between path 1 and path 3, it's 2 lambda. If you compare between path 1 and path 2, it's 1 lambda. If you compare between path 2 and path 3, it's 1 lambda. So it's always an integer multiple of lambda, means by the first path, the light wave coming out from the first slit will interfere constructively with the light wave coming out from the second slit. The light wave coming out from the second slit will also interfere constructively with the light coming out from the third slit. And the light coming out from the third slit should also interfere constructively with the light coming out from the first slit. So they all interfere constructively. Okay, so you can apply the same logic, continue to apply the same logic for the third slit, for the fourth slit, for the fifth slit, the sixth slit, the seventh slit, so on and so on. You can see that basically this is just plenty of double slit being stacked together. Okay, because they all differ by 1 lambda, so this is constructive interference. You can think about plenty of double slit being stacked together. Okay, so if you apply the similar derivation for double slit that we've discussed in the double slit video, you can actually change this R2 minus R1 1 lambda over here to be d sine theta, right? So if you are able to change it to be d sine theta, like what we did earlier for the double slit experiment, so d sine theta is equal to 1 lambda will be the equation, and the theta over here will be the theta between the let's zoom out, the theta will be the theta from here, from the center of the diffraction grating to our maxima over here. This is our theta. Okay, so this is the equation that we get if we find the path difference to be 1 lambda between each adjacent slit. Okay, for the slit beside it, if the path difference is 1 lambda, then d sine theta is equals to 1 lambda. But you know that if you go up further to the next maxima, the maxima above it, or the next maxima, you can think of it as the path difference being 2 lambda. Then this will be 2 lambda, 2 lambda, then it will be 4 lambda. Let's talk about it. If you talk about the next maxima, this will be 2 lambda, this will be 2 lambda, 2 lambda, so it will be 4 lambda, still integer multiple. So 2 lambda, 2 lambda, 2 lambda, this will be 6 lambda, also integer multiple. So on and so forth. You can see that the next maxima is formed just by changing this path difference to be 2 lambda. Okay, so if you apply the same principle and you generalize it, you see that for all the breadth fringes, for the breadth maxima that we see, it should be R2 minus R1 is equals to m lambda, not n lambda. So sorry about it. Okay, the syllabus has changed a bit. This one is m lambda, so your equation should also be m lambda. My bad, I've edited the notes, but this one is the old one. Okay, so it should be m lambda, R2 minus R1 is equals to m lambda, therefore d sine theta is equals to m lambda, where m can be 0. If you substitute m is equal to 0, I think you can see that the angle will be 0. So this is referring to the central maxima at the center. Okay, but if you talk about 1, 2, 3, then you're going further away from the central maxima. Okay, so d over here, how do you get this d over here? Like I mentioned just now, when we talk about this kind of diffraction grating, right? The diffraction grating has about 100 to thousands of slits within 1 cm. So if you want to measure using a ruler, it's definitely an impossible task. You cannot just measure it, okay, what's the distance between the first slit and the second slit? It's something that is impossible to be done using a regular measuring instrument like a ruler or a micrometer screw gauge. Those cannot measure the distance between the slit. So d is actually the immeasurable value in daily life. Of course, if you use microscope, that's a different story. But how do we usually get d here, the d that we want to substitute here? We can usually get it by doing an inverse of 1 over n. So what is n actually? So n is the number of slits per unit length. Okay, the number of slits per unit length. Okay, let me show where do we see number of slits per unit length. We have actually seen number of slits per unit length over here. Okay, so usually when you receive a diffraction grating, right, you label this one is 100 slits per cm, or this one is 500 slits per cm. So if you talk about 500 slits per cm, if you write it in terms of numbers, sorry, if you talk about n is a number of slits per unit length, right? Okay, so let's say for example, let's say n today is you have 500 slits per cm. Okay, so if you write in terms of number, this will be 500 per 1 cm. And if you want to convert into meter, because usually we do things in SI unit, then you want to eliminate cm, you want to introduce meter. So 1 meter is 100 cm. So you get this one is 50,000 slits per meter. Okay, so if you know that per meter there's 50,000 slits, how do you get the distance between the slits? Okay, so the idea here is, let's say this is 1 meter. Let's say, okay, this is just an example. Let's say this is 1 meter. Then at the same time, you can fit 50,000 slits in it. Okay, so if within 1 meter, you can fit 50,000 slits in it. So the distance between each slit will essentially be just taking the 1 meter divided by how many slits you have, right? If you take this 1 meter, divide by how many slits you can find within this 1 meter, you find that each slit will take how much space. So each slit take how much space is basically the distance between the slit. Okay, you can think of it maybe not the same, but it's actually roughly similar. Okay, so just by taking 1 over 50,000 over here, you are able to find the distance between the slits. And that's why the distance between the slits is equals to 1 over the number of slits per unit length. Okay, so usually d is not a measurable value, but what can we do? We can substitute d 1 over n to replace a d over here. Okay, so you need to be flexible. If you have information regarding D, then it's good. But if you have no information regarding D, you can obtain it from 1 over n. No problem with that. Okay, so now let's move on, talk about the m. The m here, there's 0, there's positive 1, positive, negative 1, plus minus 2, plus minus 3. What does it refer to? Well, if this is your diffraction grating pattern, then the central maxima here will be referring to m is equals to 0. So of course the next one here will be m is equals to positive 1. Okay, so if this is m is equals to positive 1, then this angle over here will actually be theta 1. Okay, if you go to m is equals to positive 2, which is further up, then the angle will be theta 2. Okay, if you go up further to the m is equals to positive 3, then you get theta 3. So basically that's the idea of how you count the order. Of course, if you go below the central bright, you count it in negative, but that's not really important. So that's it for diffraction grating. Thank you very much.